This video is created as a part of MEMS device fabrication project for the course ME509 offered in Washington State University. This is Jennifer Anand, graduate student from University of Idaho, who created this video and narrating this movie slides. The title of my project is Individual Zinc Oxide Nanowire Biosensor for Urea Detection. Before getting into the details about the project, let's see why a urea biosensor is needed and also why it is needed in MEMS scale. Keeping body chemicals present in blood like glucose, cholesterol and urea in balance is very important for health. People with extra weight, diabetes, heart diseases or high blood pressure have high possibility of increased urea concentration in blood. Increase in urea concentration in blood can cause severe outcomes like kidney failure, which in turn call out for kidney transplantation or hemodialysis treatment. It is therefore very essential to know and control the urea concentration in blood for the patient. Oftentimes, unexpected increase in urea concentration has caused discomfort and severe outcomes. Therefore, determining the urea concentration before it reaches the critical level and alerting the person is very significant as it can avoid severe outcomes. The requirement can be met only by a biosensor at micro level because it turns out to be a cost-effective and compact device. A glucose meter or a glucometer is a medical device that is more widely used for determining the approximate concentration of glucose in the blood, which keeps and helps the person to take necessary steps if they are above the limits. Like glucometer, cholesterol meter is also a medical device for measuring cholesterol in our blood. It is very important to know the cholesterol level, as cholesterol increases the general risk of developing heart diseases. As we already know the severity of increased urea concentration in blood and its serious outcomes, it becomes very essential to have a user-friendly urea meter which can update us on the blood urea concentration. Principle behind the urea biosensor. Urease is an enzyme that catalyzes the hydrolysis of urea into carbon dioxide and ammonia. The reaction occurs as shown in the slide. The released ammonia gas gets absorbed on the surface of a single zinc oxide nanowire, thus changing the electrical conductivity of the wire. The change in conductivity can be accurately calibrated to read the urea concentration in blood. Device overview. As shown in the figure, when the blood comes in contact with the enzyme urease, it helps in the hydrolysis of urea in blood, which releases ammonia gas. A part of this urease is exposed to blood and the other part is enclosed inside a cavity which contains the single zinc oxide nanowire, whose ends are embedded to the electrodes. When the zinc oxide nanowires are exposed to the ammonia gas, it absorbs the ammonia gas to the surface and behaves like a field effect transistor, which in turn affects the conductivity of the nanowire. At this stage, when a certain voltage is applied between the electrode gates, the flow of current varies based on the concentration of ammonia absorbed. This change in flow of current is sensed, amplified, and calibrated to read the urea concentration in blood. Here, the sensitivity of the biosensor depends on the nanowire dimensions, gas concentration, and applied gate voltage. On account of these facts, the design constraints have to be finalized for designing an ideal urea biosensor. Design constraints. The constraints involved in this project and the probable solutions to overcome it are discussed in detail. For high sensitivity, excellent change in conductivity, and for the best results of the sensor, the following are very essential. Concentration of ammonia gas should be in the range of 10 to 30 parts per million. As a dimensional constraint, the diameter of zinc oxide nanowire is expected to be between 50 to 60 nanometer, and the channel length of the zinc oxide nanowire is expected between 7 to 10 micrometer. The voltage applied has a significant effect on sensitivity because it directly depends on the gas concentration. For 10 SCCM of gas concentration, the best sensitivity is between negative 1.4 voltage to negative 2.4 volt, where 2.2 volt is the threshold voltage for 10 SCCM gas concentration. Steps involved in designing a single zinc oxide nanowire field effect transistor and fabricating the device are quite challenging. Refurbishing the process in designing will help to solve the issues involved. This foundation will be a good start for further progress in the project and fabrication of the biosensor. Here are some references about the project. Thank you for your kind attention.